Hello, everyone, and welcome to our webinar, LLM Review Use Cases for OpenAI, Gemini, Llama, Mistral, Claude. My name is Yukti Dwivedi, and I'll be your moderator today. One of my main jobs at SingleStore is to organize weekly AI webinars. We organize 2 webinars per week, and one of my main jobs is to bring these webinars to you guys and be your moderator. I'll post about all these upcoming webinars every week. So if any of these topics are interesting to you, please feel free to connect with me on LinkedIn to stay on top of the loop. I'd also love to hear your feedback or any ideas or suggestions that you guys have on topics that you would like to see in the future sessions. Also, speaking of future sessions, we have got several amazing, great webinar sessions coming up. On May 16th, we have Beginner's Guide to RAG with Professor Tom. And on May 17th, it's a very in-demand topics. It's called GPT-4o for developers, hands-on with OpenAI Spring release. On May 20th, we have how to build local LLM apps with Llama and SingleStore for Mac security. If any of these topics are interesting to you, please RSVP right now. You can see the QR code on your screen, and please register, and I hope to see you all there. Also, you'll notice that now we have a feature called Auto RSVP to future AI webinars. We have this option on our website. So if you visit any of these landing pages, there's now a checkbox to auto register, which will add future upcoming Zoom sessions automatically to your calendar, which obviously you don't need to join each webinar live, but this is an option for those who have requested to automatically receive the video recordings and GitHub links to whoever finds these sessions useful can. The new free share tier, which we'll talk about a bit later today. A lot of people have been leveraging it, and we have heard some really nice feedback about it. So do check it out. Moving on, I am very excited to announce our speaker today. Joining us today is Ayush Pai. He is a computer science student at Georgia Tech, and we originally met him online after he created the viral AI basketball referee demo. Since then, we have partnered with him on a few projects that demonstrate the power of SingleStore DB for different industrial AI use cases. We are so happy to have you, Ayush. Thank you, and the floor is now yours. You can take over.
Awesome, thank you. Akmal, do you want to take the first couple slides for SingleStore?
Yeah, thanks very much, Ayush. Yes, so here we can see a little bit of background on SingleStore then. So as we can see, I mean, the company goes right back to 2011. And over time, both the revenue and the number of customers have increased. So revenue really started to increase significantly between 2017, 2018. We are today $100 million ARR company now, annual recurring revenue. And you can see that the number of customers there, over 350 global customers. And again, the number there started to increase significantly between 2019 and 2020. And along the bottom there, you can see very well-known names in terms of the investors within SingleStore, brands that you will probably recognize from all over the world. Okay, thanks, Ayush. Next slide. Okay, so just a little bit on the architecture. So this is a nice kind of high-level overview of what SingleStore is. So at its heart, you can see in the purple box there, universal storage, so the ability to handle both OLTP and OLAP. Fairly unique in the industry. Others are trying to do this, but we've had this capability for some time now. And then on the left-hand side, you can see fast ingest plus CDC. And in the recent past, we've covered Apache Spark, for example, for transformations. We've covered connections to Apache Kafka as well. And then we can consume from other sources such as HDFS and Hadoop. Along the bottom, you can see that we work with all the major cloud providers in the Western world, AWS, Google Cloud, Microsoft Azure. You can run on-prem as well if you wish. And if you create an account on the portal within the, on the left-hand side, on the left navigation pane, you'll see that right down at the bottom, there's an opportunity to actually get a license, which will allow you to install a 4-node version free of charge. And that's the full product. The only limitation is that just the number of nodes, and you can install that yourself on-prem, in the cloud, anywhere that's convenient for you. On the right-hand side, you can see the stored data type. So relational is at its heart, but we do other things as well, geospatial, full text. key value JSON time series, and of course vectors, very popular topic today with the kind of long-term memory for LLMs. And keep in mind that SingleStore has had support for vectors actually since 2017. Better support for that this year, introduced with a dedicated vector type, as well as approximate nearest neighbor indexing, and lots of other cool features as well, which are documented. And then finally, just variety of applications, real-time analytics. And so if you look at this big picture, because we often get asked the question, how is SingleStore different from, say, Pinecone or Weaviate or ChromaDB? Well, there is the difference. Okay, so we do far more than those products can do in terms of the kind of connectors that we have, the variety of sources that we can consume, the different platforms that we can run on, the data types that we support, okay, not just vectors. So you can use SingleStore as a pure vector database if you want to, but typically in enterprise environments, customers want to do more, okay, and they have more requirements in terms of the type of data that they're processing. So there we go. And I think that's it from me. I think, so hand back to you, sir, and give you the rest of the time. Thank you very much.
Awesome, thank you. Thanks for that great introduction. And let's actually just hop straight in, right? So today I'll really be presenting about an in-depth review of large language models, comparing various models, OpenAI, Mistral, Llama, all these different models and their use cases. But let's just start off with a brief introduction to AI and build our way up. So AI kind of refers to the simulation of human intelligence in machines, really enabling them to perform tasks that really typically require human intelligence, such as learning, reasoning, problem solving. And I would say in our day and age and what we're seeing today, we're going to really talk about three of these fields. So machine learning, natural language processing, and computer vision. And these are kind of three field subsets under artificial intelligence. So machine learning really focuses on the development of algorithms that enable computers to learn and make predictions based on a data set. An example is a regression analysis where the model identifies a relationship between a dependent and independent variables to make predictions. Natural language processing really involves an interaction between computers and human language. It really enables machines to understand and interpret and respond to human language. And this is really essential for applications that we're going to see today, such as chatbots and language translation devices. Computer vision is a field that deals with how computers can be made into high-level understanding from digital devices, digital images, or digital videos. Enables applications like autonomous cars and facial recognition systems to really understand their surroundings. And understanding these fundamental elements is crucial as we kind of delve deeper into the specifics of LLMs and their architectures, and really exploring the different modalities that we're going to see today. So as we dive deeper, just a quick history of AI. So one of the more notable early AI programs that we saw was the Logic Theorist, developed in 1956 by Alan Newen and Urban Simon. And this was deemed the first AI system ever, right? And this was designed to mimic problem-solving skills of a human, proving mathematical theorems by applying logical rules. Basically, what it did was it essentially demonstrated that machines could be used to solve complex problems through logical reasoning. You can see those, yes, no, and gates right there. Kind of like just very basic, logic that it was used, and it was, deemed the first version of artificial intelligence. Obviously, maybe 30, 40 years later, we had IBM's Deep Blue, and this was really a really significant advancement in AI and just computer science in general. And really, what happened was Deep Blue, this computer system, was defeated the reigning world chess champion Garry Kasparov, and showcased AI's potential to handle complex and strategic tasks that were previously thought to be, exclusively of the human domain. And Deep Blue's victory was not just a triumph of computing power, but also a testament to the sophistication of AI algorithms and decision making and problem solving. And as we look forward onto these new technologies that we have today, it's important to just kind of see where we came from. So I could journey to large language models, right? So I think there's three main things that we need to discuss before we get there. So actually these are just four like high level overviews that kind of take you step by step through the architectures, that lead up to large language models, right? So we begin with neural networks, which are these graph-based structures that are designed to mimic the human's brain's architecture. These networks really enable machines to recognize patterns and make predictions by adjusting weights through training processes. Next, we have recurrent neural networks, and these are where we introduce loops into the network, allowing the information to persist across time steps. And you think about it, this is very important for different applications, such as handling sequential data, such as text and time series. If you think about a stock market, if you want to predict what comes next in the stock market, you want the sequential data of the past. If you think about, large language models, essentially what they're doing in the back end is detecting, based on all this context that you have, what word comes next and giving the highest probability of the word that comes next. And that's kind of how these large language models work. But these RNNs really struggled with these long-term dependencies, and they had this thing called vanishing gradients, which I won't get into today. But to kind of address these limitations, long short-term memory networks, LSTMs, were developed, and these are a type of RNN that can learn long-term dependencies more effectively by incorporating mechanisms to retain information over an extended period of time. And the most significant advancement came from the introduction of transformers in 2017. So transformers really utilize self-attention mechanisms to process entire sequences of text simultaneously rather than sequentially. And this innovation has led to substantial improvements in natural language processing and is the architecture behind all of these large language models that you see today. And the developments of neural network architectures have paved the way for the development of LLMs, as we see, and which we'll explore in the next couple slides here. But just to kind of allowing you to understand how these neural networks work just really quickly. So essentially what they're doing is they consist of these interconnected layers of nodes, also known as neurons, where each layer transforms the input data using weights and biases to produce the final output. So a typical neural network architecture includes an input layer, one or more hidden layers, and an output layer. And the process begins at the input layer where the data is fed into the network. So essentially the data is then transformed through the hidden layers using activation functions, which introduce nonlinearity into the model and allow it to enable to learn these complex patterns. So each neuron in the hidden layer is connected to every neuron in the previous and subsequent layers, and it forms this dense network of connections. Training a neural network involves using a large data set of optimization algorithms like gradient descent. Gradient descent actually takes the weights so the weights are actually these lines that connect one neuron to the other, and that kind of predicts what's going to be in the next layer and ultimately what's in the output layer, which is your final prediction. And gradient descent adjusts these weights and biases to minimize the error between the predicted and actual outcomes. And I'll kind of go over this in the next slide here. But to train a neural network, data sets are fed into the network by representing the inputs as numerical features. For example, consider this image of a tiger, right? This image is converted into a grid of pixel values or whatever numerical features you want to represent it by, and then it's fed into an input layer of a neural network. These numerical features kind of pass through the network's layers, where each layer applies a series of transformations using weights and biases. And the output of the final layer is compared to the assigned label. So essentially, we have these randomized weights and randomized biases that these numbers are fed through the network through. And the output layer is going to basically give you a prediction. It's going to be one prediction in the final neuron, and it's going to be, what tiger or whatever it detects, whatever classification label that it detects. And essentially, what you're going to do is the goal is to see like what the difference between that is and your actual label. So if you get something that says lion, or something, it's probably going to be something more abstract, such as like a vector. You want to see how far away that vector is from the actual result, and that's called the loss. And basically, your whole goal is to minimize this loss through the training. And optimization algorithms like gradient descent are used to adjust the weights and biases to reduce the error iteratively. And kind of so there's kind of like 2 or 3 stages mainly in this neural network training process. So the forward pass of the neural network, the input values are first fed into the initial layer of neurons, known as the input layer. So each neuron in this layer receives one feature of the input data. And the process of forward propagation involves passing these inputs through the network layer by layer to generate output, right? So for each neuron in the subsequent layers, the values are calculated by taking the inputs from the previous layer, multiplying each input by the corresponding weight, and summing these products together, with a bias term. Mathematically, you see this formula here. It's Z equals W times X plus B. This is a simplified way of representing this, what you're actually calculating here. But what you're doing is you're taking this weights, which is a weight matrix, which if you see like this network here, the weights matrix kind of represents the, each connection to the next node. So you have, X node to X node in the next layer. And you need a matrix to kind of represent that entire weight representation. And so that's what that weights matrix is. So you're doing a matrix multiplication. So you're taking that weights, you're multiplying it by the vector of input values, which is just a one-dimensional vector of all your inputs. And then bias is the bias vector to bias term, and it's just a simple one-dimensional vector that you add to that final result. And then you get this weighted sum, Z. And then Z is passed through a nonlinear activation function. And essentially, what this is doing is activation functions include something like a sigmoid function, tanh, or relu, which means rectified linear unit. And it introduces nonlinearity into the model. And essentially what this means is it allows it to learn complex patterns and relationships in the data. For example, the relu function outputs the input directly if it's positive, otherwise it outputs 0. The tanh function gives you values from 1 to -1, and it basically you can put in any value. You can put like 100,000, and it'll give you a value from 1 to -1. And the tanh gives you, or sorry, that's a tanh, and the sigmoid gives you a value from 0 to 1. And this is crucial for the network's ability to approximate complex functions, because you can't really, take really, really high values. If you get like a really, really high value, like 100,000 or something in this network, you don't really want to have that. You want to have it represented between 0 and 1, or -1 and 1, or whatever you're trying to do. And by repeating this process throughout the layers of the network, the input data is transformed and refined, producing the final output of the layer. So once the forward pass is completed, the output layer's values are fed into a loss function. And this difference, so basically this loss function is going to measure the difference between the predicted values and the expected values. So the expected values is kind of what you see with this label here, right? You have this label of a tiger. That's the expected value. Think about tiger more of like as a vector representation. So you have a vector and you're trying to see how far away, or even just think about it as a number. Think about it as 15, right? And you want to see how far away it is from your actual output value. If your output value is something like 12, so that means your loss is 3. That's a simple way of representing it, but that's just saying it's kind of a measure of how far off the model is. And there's there's a lot of different ways of calculating this. Some kind of general ways is mean squared error is commonly used for when you're doing regression tasks, and for classification tasks, cross entropy loss is often employed. But here's the formula for mean square regression, mean square error, sorry. And so yeah, minimizing the loss function during the training helps to improve the model's accuracy by kind of reducing how far off these values are, and helps improve and basically guides the optimization process to adjust the weights and biases effectively. So the core of the neural network model is performed through a process called backpropagation. And this is a critical step where the model really learns to adjust its weights and biases to minimize the loss calculated in the previous step. So this loss is what you want to minimize. You want this to be as close to 0 as possible. And this process here called backpropagation is where it actually takes all those weights and biases and uses those to adjust them to make the output layer make the best possible values that perform like the least amount of loss. So for each neuron in the hidden layers, backpropagation involves calculating a gradient, which indicates how much the loss would change with respect to the change in the neuron's weight. This is achieved by computing a local gradient, which is the derivative of the activation function, kind of like the tanh, the relu, or the sigmoid at the neuron, and multiplying by the gradient of the loss of the layer above. And the application of the chain rule propagates the error back through the network all the way back to the start. And all the weights are adjusted by these gradients, or basically just derivatives. Once the gradients are calculated, the weights and biases are updated using an optimization function. A common optimization technique includes stochastic gradient descent and Adam optimizer. Here's a formula for stochastic gradient descent. So basically, you're taking the weight of what the weight currently is, and you're subtracting it by something called a learning rate. So that's basically like a decimal number, kind of representing how much you want to change in every step. You don't want to change it too much every time because you're running it multiple times, but learning rate can be like 0.001 or something, kind of representing how much your rates are going to change in each step of gradient descent. And this is basically the gradient. So the triangle here is the gradient, and it's kind of the step in the direction of which way you're going for your weights. And kind of on the left side here, you kind of see how these weights are kind of calculated, or the gradients are kind of calculated. Basically, you're just taking, it's from each step of the network, you're taking a gradient, which is basically just a derivative, and then, propagating it backwards and just multiplying it. So, and that's neural networks, right? And they might seem a little bit confusing at first if you've never seen this kind of architecture before. But with some time and a review of derivatives and just looking at it once or twice again, watching this recording, make a lot more sense, right? And fundamentally, the idea is simple, right? You start off with this randomized networks of weights and biases. You input your data set through the network. You measure how far off the output values of the labels are using a loss function, and then you update the weights accordingly using backpropagation and optimization techniques. And yeah, and you just keep doing that. It's a repetitive process until you have the least loss possible, or your epochs are done, whatever. Yeah, and through this iterative process, the model learns to make accurate predictions. With the model now trained, these learned weights can be used to process real data and produce reliable results. And yeah, that's how neural networks work. So let's get into these other architecture really quick, and then we'll get into LLM. So RNNs are specifically designed to process sequential data. So this is really important for these LLMs. So neural networks themselves don't process sequential data. They don't really take what's before and consider it all. So they're specifically designed for the sequential data, and unlike traditional neural networks, they have loops that allow them to retain information from previous inputs, creating a form of memory that captures context. However, these RNNs struggle with their long-term dependencies, as I kind of said earlier. These problems occur when gradients become too small or too large, and kind of showed what gradients are before. When the derivatives become way too big or way too small, it can completely throw off the network. And this is called, vanishing gradients or exploding gradients. And despite these challenges, RNNs are super effective, and they're a really great foundational architecture, and they kind of pave the way for a lot of these other architectures that we see. So LSTMs, or long short-term memory networks, are designed to overcome the limitations of RNNs by introducing memory cells that can maintain information for long periods of time, really effectively capturing long-term dependencies. So the architecture of LSTMs includes gates, so there's three main gates. There's input, forget, and output. And that controls the flow of information. So these gates really allow the network to decide which information to keep at every step, or forget, and then output into the next layer. And it really allows it to retain relevant information over long sequences and improve performance on tasks that require long-term memory, such as like large language models, language modeling, time series prediction, whatever that needs that long-term dependencies for. And finally, transformers are these architectures, again, behind large language models. It kind of is the successor to LSTMs. And the really cool thing about these is the really key feature here is they use this thing called a self-attention mechanism that allows it to weigh the importance of different words in a sequence, allowing them to capture relationships and context over long distances without relying on sequential processing. So unlike RNNs or LSTMs, transformers really process input data in parallel. So needs a lot more GPU and processing, a lot more compute, but it's a lot more efficient in terms of large data sets and scalability. The transformer architecture employs an encoder-decoder structure for their architecture, where the encoder processes the input sequence to create this rich representation of the words, and then the decoder generates the output sequence based on the representation. And yeah, now that we've covered the prerequisites, let's dive right into all LLMs. And so LLMs are really trained on a vast amounts of text data from diverse sources, really enabling them to learn patterns, context, relationships within the language. So these models leverage the transformer architecture, which we discussed a little bit earlier today. They really efficiently process and generate text. So essentially, the training process for these LLMs begins with a pre-training process, which is on a large corpus of text using self-supervised learning. This helps the model to really learn general language representations. And after pre-training, these LLMs are often fine-tuned on specific tasks for domains or use RLHF for human feedback integrated directly into the network. And fine-tuning really enhances the performances of these networks for particular applications for sentiment analysis, question answering, language translation, etc. And by combining the broad knowledge gained through the pre-training process, through the transformer architecture, with the specialized skills learned through the fine-tuning, LLMs can really be adapted to a wide range of tasks, demonstrating a remarkable and really versatile in natural language processing and a lot of other applications as well. So kind of getting into some of the LLMs that we see today, right? Kind of the topic of this presentation is we have these LLMs. We're talking about 5 of them today, 5 providers. So we have OpenAI, Google, Meta, Anthropic, and Mistral. And it's kind of important to kind of understand the difference between these and really what their strengths and weaknesses are. So OpenAI is probably the most popular, the one that you've seen the most in the news, headlines, stuff like that. So they have the GPT line of models. So they start off with GPT-1, which is the president's, it's kind of really a good breakthrough to the time, but really no one knew about it. It was until GPT 3.5 that ChatGPT came out and took the world by storm. But GPT-1 was a kind of predecessor to BERT, which was created by Google. And it was an advancement on that type of transformer architecture. So they had GPT-1, 2, 3, 3.5, 4, and actually on Monday, they released GPT-4o, which we'll talk about in a little bit. And we have a presentation this Friday, which you should definitely register for that on GPT-4o, all the new updates and what the new capabilities of this newest model are. We have Google's models, so they have Gemini, they have 1.0 Pro, 1.0 Pro Vision, 1.5 Flash, and 1.5 Pro. And they also have their Ultra series, which hasn't been released via API yet, but soon will. And I think that's their flagship models. And they also have these Gemma open models. And we'll talk about what the open versus closed models are in the next slide. But we also have, next we have Meta, which they have their Llama series of models. So they had Llama 1, 2, and recently 3. And these are also open models. We have Anthropic, which has Claude 3 Opus, Claude 3 Sonnet, Claude 3 Haiku, and and Opus is their obviously most powerful model, and then Sonnet is their second most powerful, and then Haiku is their, I think, minimal model. Everyone has this similar trend of having these big models, medium models, and small models, and those are all closed models. And Mistral line of models. So Mistral is another company that makes these open models, but they also started getting into these closed models more recently. So they have their 7 billion parameter model, 8 by 7 billion, which is kind of the mixture of experts models, and also 8 by 22 billion. And they also came into the closed source world with Mistral Small and Mistral Large. So when discussing LLMs, it's really important to consider the distinction between open and closed models. So closed models are developed and maintained and also owned by specific entities or organizations with their underlying code and training data kept really proprietary. In contrast, open models offer transparency, customizability, and really collaborative development environments that and their source code is, a lot of times available, and also their pre-trained model weights are also available for anyone in the public to download, run locally, and freely available for anyone to use, modify, or build upon, or fine-tune, whatever they want to do. This openness really fosters innovation, allows the community to contribute, and improve the models and make them more versatile. So it's good to see more and more companies going into this open model space because then we don't need to rely on an API from those companies and then have to pay for every token that we access. It's something that we can run locally or run on our own computing services instead of relying on another company's requests. So here we kind of compare the benchmarks of various large language models across multiple metrics here. So the table highlights key performance indicators such as average score, multiple choice questions, reasoning, Python code, feature capabilities. And, it kind of shows all these different categories here. And notably, Claude 3 Opus and GPT-4 really excel in reasoning and multiple choice questions, showcasing their robust and complex problem-solving skills, and general knowledge tasks in general, because they have the biggest models, obviously. Models like Gemini 1.5 Pro, obviously a lot smaller of a model, compared to GPT-4. And Llama 3 Instruct 70 billion also have performed really well, particularly in Python coding and future capabilities. And these comparisons kind of provide a comprehensive overview of the strengths and areas for improvements in each models, and really allows you to guide your decisions on picking which LLM is best for you based on which application you're going for. And these benchmarks are available all online. This is just one of the websites that I found. There's also the Hugging Face Open LLM leaderboard, which is a really, really cool thing, because essentially what it is they have a leaderboard of all the top open source LLMs. And basically, it's like a leaderboard to get to the top. Who can make the best open source element? I think that's a really good way of promoting open source and allowing, developers to contribute as well. And this table shows the performance of various closed LLMs across multiple benchmarks using 5-shot learning. And 5-shot learning is when the model is provided with 5 examples for each task before making predictions, helping it make a better understanding before the task requirements. So Claude 3 Opus, GPT-4, and Gemini 1.0 Ultra all kind of show this strong performance across these categories. This is, Opus kind of really excels in grade school math, common knowledge. GPT performs well in undergraduate knowledge and reasoning over text. These are some really cool, ways of understanding how these models are built and which ones have the best accuracy. MMLU is kind of like a industry standard kind of way of understanding how good a model is and how good it is. But obviously, these benchmarks are not the only thing you should be looking at when choosing which model you should be using. It's also based on other things as well. And one of those other things is context window. So context window measures how many tokens a model can take in as a prompt. So for example, if it's a really small context window, maybe you can only put like a paragraph. But if it's a really big context window, you can put like a book or like a textbook or like, I don't know, something really big, right? General rule of thumb of how these tokens work is approximately 0.75 tokens per word. This is just an approximate. It could vary from model to model, but as we can see here, GPT-4o, latest model from GPT, has 128,000 context window. Gemini 1.5 has a 2 million context window, which was actually released yesterday at Google I/O. Previously, they had a 1 million context window. Claude 3 models have a 200K context window. Llama 3 models have 8K context window, and Mistral models have 8K context window as well. Those open source models have a little bit less, but also they're open to use and a lot freer. So another thing that you want to kind of decide when you're trying to figure out which model you want to use is their multimodal capabilities, right? So as LLMs continue to evolve, offering advancement capabilities and kind of shaping the future of AI, key areas of development include improved reasoning abilities, enhanced contextual understanding, and more efficient ways of understanding data of the real world. And one of those ways is to kind of really increase the number of modalities that the model is equipped for. So GPT-4o is a combined text audio visual model that came out yesterday or Monday. And a lot of these models, they used to be multimodal, and we had multimodal in quotation marks. And what that means is because they had a text model, they had a voice model, and then they had an image model, and they combined those two together, and it was cool, like to see, you can upload an image and then get a response, and you can talk to it and get a response, but there's a delay, right? You can obviously there's a delay because it's multiple models, they have to do multiple requests and whatever like that. So this new thing is the GPT-4o released yesterday, and for more details, come to the presentation on Friday, is that they have these combined text audio vision models that are combined all 3 modalities in one neural network. And Gemini models, that was their whole goal from the beginning as well. They were built ground up as multimodal models with text audio vision capabilities. And you can see from that Gemini, the GPT-4 demo on Monday, how quickly it was able to respond to voice commands and how quickly it was able to understand like what your camera sees and stuff like that. The Claude 3 line of models are also multimodal. And Mistral and Llama are currently not multimodal, but it'll be really cool to see, open source multimodal models. And there are a couple out there. I'm not sure how good they are, but there are a couple out there, but it would be cool to see them from Llama and Mistral as well. Awesome. So now let's get into some code and a demo. So I believe the GitHub should be sent. If not, I can send it really quickly. So we can follow along with this GitHub that I just sent in the chat. And yeah, so let's go through. So essentially I have a notebook. You can run it in Colab or wherever you want. But yeah, so essentially what we're going to be doing here is kind of looking through these models, seeing how they work, and understanding like their capabilities and kind of comparing the differences between their outputs and seeing which one would be the most capable for what you're trying to do. So the first step is to just install these libraries. We're using OpenAI, LangChain, and Pandas, and that's mainly the LangChain is a great way of accessing all the models through one API. Really great way of doing that, and also has a lot of capabilities with vector, really customizing your input. They have this whole library directly for inputs into an LLM called prompting. And there's a lot of cool things you can do with LangChain, but specifically here, we're going to be using it for accessing multiple APIs with one. So the next step what you want to do is put your API keys in here. For me, I'm accessing them directly with so I'm using Google Colab to do that. So you can put your API keys here. I actually want to just put mine in really quickly and have them not be on the screen. So just give me one moment for that. Okay. So yeah, you would just put in your API keys here. So we're going to be using these three APIs for today: OpenAI, Google Gemini, and Anthropic for Claude. And so I'm just going to access them directly from here. So I'm just going to do user.data. I think it's just OpenAI.
Are you showing a different screen? We'll just see your slides there. Did you switch? Ah, there we are. Thank you very much. Thank you.
Yeah, just putting these in really quickly. Sorry about that. I took them out just so that they weren't in the GitHub. And finally, this one for Anthropic. Okay, cool. So yeah, so once you do that, you'll have your API key set up. And now these next steps here are just testing out the APIs directly with LangChain. So you have LangChain Anthropic chat here, where you're loading the model in. We're using Claude 3 Opus, which is their highest tier model. And then you can set some other parameters such as temperature and set your API key here. And so essentially, you can put in your prompt. So we have a system and a human message. You're just a helpful assistant. Explain neural networks in 2 sentences. What is not defined? Interesting, because it's right defined right here. Let's see if I think I need to just refresh the notebook. Yeah, let's just run through this one more time. And yeah, so I'm just doing the same thing over here as well for OpenAI, and I'm doing the same thing here for Google. I'm just testing out the LangChain integrations directly with that. I'm not really sure what the issue is here. We can move on from that, come back a little bit later, but
We have some people pointing out that you have misspelled Claude. Just if you can check that.
yes, I can check that. Yep, that seems to be the issue. Thank you.
Eyesight must be really good. I'm wearing glasses and I can't see it.
Okay, cool. So we get this output right here. Neural networks are types of machine learning, whatever. On the output, we have our output from GPT, similar output. Kind of a really similar response here. I mean, they're similar models. You don't know what their data sets are trained on, but obviously you're going to get a pretty similar response. If you're explaining in 2 sentences, similar thing with Google. Really thing about Google is actually they have this thing where they provide these metadatas about the prompt, and it gives you feedback about the prompt as well. This is really cool because as like a developer, you can really see and understand how these prompts are working and really understand, like, are they safe prompts from the user? Are they negligible? So there's some categories here that you can look at. You have hate speech, you have all these categories, harassment, stuff like that, dangerous content, and it gives you a probability based on, true or false, as well, based on like if it should be blocked based on the prompt. So if you put something really bad into the prompt, you can also see these categories here, based on like the prompt itself. So it gives you feedback on the prompt, which is really cool. But yeah, so we have this next part here, which is going to be, we're actually going to define these models that we kind of already did earlier. So just had just a declaration there. But what we're going to do here is we're going to actually, define some questions and answers. And we already know the correct answers to these questions, right? So we say, what is the capital of France? Explain the theory of relativity in 2 sentences. What is the derivative of x squared? Translate blah blah blah, right? And we have the answers in this other other thing right here. And we're going to create a data frame out of these questions and answers. And essentially what that's going to do is allow us to compare, how their output responses from these different models based on these correct answers here. And so this part right here is going to be generating the model's outputs. So we have all these things imported again. We have the definitions for these models. And what we're doing here is we're going through all these questions and then, saying to answer these questions based on, the ones in this list. So let's go through this and run it and see what it does. So the first thing that we're doing here is for GPT. It's going to put it in this thing called GPT responses. And see how it does. I think it's running Claude now. Cool, and it saved it to the CSV file. So let's open the CSV file and see how it did. So yeah, so let's see what these, okay, so we got some errors from Gemini for some reason, but that's okay. I think it's some developer issue or something with the API maybe, but we got something from GPT and Claude. So this is the correct answer that we have. They have this answer right here. And Claude has this response. So this is a good way of just seeing, like, based on these generic questions, you have questions about history, you have questions about theory of relativity, you have math questions. These are how you can do some evaluation frameworks and make your own based on your own use cases here. So yeah, we have all these different responses, obviously a lot longer than what they were expecting here from the expected answer, but you can tune how long you want your answers by just setting it as a parameter. And yeah, that's a great way of doing that. And what you can do from this is you can actually determine how far off the answer is from GPT or Claude or Gemini to the correct answer. If you have the correct answers, what you can do is you can do like a similarity between the two, maybe like a vector similarity. So what you would do is you would represent it as a vector using an embedding model. You would represent the correct answer and then the LLM response as an embedding. And then what you do is you do something like cosine similarity, or something like some way of determining how close the two vectors are. And that'll give you like a similarity score. And based on that, you can figure out which model is best suited based on the typical responses that you might have in your application. And yeah, so that's just showing, how we can represent correct answers and see like what the actual models are predicting, and kind of see the difference between those two. Here we're just testing multimodal capabilities. So we have this image right here. It's just a generic image of just a scene. And what we're going to do here is we just test out between Gemini and OpenAI, what their differences and the responses are here. So OpenAI says this image is a scenic landscape with wooden boardwalk, blah blah blah. Cool. Yeah, probably seems right? Cool response. And then Gemini, I guess we have this write a story. So let's see what it does. Write a story about this scene. And yeah, I guess it, gave the story here. Yeah, I don't know. It's cool, whatever. Yeah, it's their story, and you would just input the image here. So there's two ways you can input it by like a URL, or you can input it by an image. You can do whatever works best for you. The last thing that I want to show here is kind of retrieval augmented generation versus this long context length. So you know, with this new context length from Gemini with 2 million context window, kind of crazy, right? You can put in kind of what they said in their demo, so that you can put in like 2 hour-long movies, or you can put in whatever, like you can put in like huge textbooks, huge corpuses of data, and then ask like one simple query, and it'll go through all that data and find the answer. So I kind of wanted to see, like, you know, what's the difference between this long context length and retrieval augmented generation? If you don't know, retrieval augmented generation is a process where you basically take the document that you have. So instead of putting it into the prompt, that huge prompt of like a million contexts, you just put it into a document, and then you basically vectorize that document, and you would put it into a vector DB. And then from that vector DB, you would essentially, whenever you get a prompt from a user, you would do a vector search in that vector DB, find those similar documents, and then basically return it to be inserted into the prompt. So it's a more complex process, obviously, than having it directly integrated into the model. But let's see, like, you know, performance-wise, which one does better. So this is, you know, we're using Gemini here. We have this pretty long, this is a Wikipedia page of the 2024 Super Bowl, and it's a pretty long document, right? A lot of random stuff. Obviously wouldn't fit into like a generic large language model, you know, like a Llama or one of these smaller context lengths. But since we have 2 million here, could probably do a lot more than this, honestly. But let's see what a result. So I'm basically saying answer based on the content, 3 sentence backs, which celebrities were at the 2024 Super Bowl. And then the human thing is the text content, which is got from the document. And here it seems to just be giving some generic information. I'm not really sure why it's doing this. It's just giving some generic information. Maybe if we put it directly into the human prompt itself, it might do better. It might be some prompting thing. But it seems a little bit different. Let's see what it does if I put it directly into the human prompt, right? So we have you know, this prompt here, and then we're going to say plus this, and we'll just delete the system prompt. And let's see what it does, if it's any better here. Okay, so it just wasn't able to get it, right? And it's using the provided text. So not really sure. Maybe it's just not capable of doing so, but let's do the RAG test here. So RAG, essentially what I'm doing here is I'm using SingleStore DB as our vector database. Essentially right here, let me just put my my URL in. So this would be your connection to your database and SingleStore, and you can see my SingleStore portal here. So essentially what you're doing is you're setting up your SingleStore database, your connection right here, and then you're using LangChain to basically load this text document in into our text loader, which is a native object in LangChain. What you're doing with that loader is you're loading these documents, you're splitting it based on a certain chunk size. So every 2,000 characters or so, which it splits this document, so it's not all in one huge document. And essentially what it's doing, it's generating these embeddings using OpenAI. You can use any embeddings model, you could use Google, it doesn't really matter in this case. But you know, you can then, what we're doing is defining this docu-search, which is basically a variable for our vector DB. And you're creating this new, you're creating this new table here. And this table is going to have these two columns, which are the documents and then the embeddings themselves. And yeah, so this part is just our chatbot loop, which is essentially you go into this loop, and then while get the user's query, then you would get the similarity score between the user's query and find the most relevant document. So you're doing document 0, which is the most relevant document with the highest similarity score. And then you would initialize the model and then put the user query plus the context into the model. So the context is directly from that vector similarity search through the vector database. And yeah, let's just see how this works. Now, I'm going to run this, and you can see in the vector DB here for SingleStore, we have our content and these vectors. That these vectors are generated. You can't really see them well here in this representation, but they're huge multi-dimensional vectors. I think OpenAI has probably like 128 and probably more dimensional vectors. And Let's see. So we have this chatbot interface here. Now let's ask kind of a similar question, right? So I said, which celebrities were at the 2024 Super Bowl? And let's see if it does a better job than the context length. Okay, I mean, it gave a response, Beyonce and Tony Hale. I can say any more. Okay, a bit of a hallucination there. I'm not really sure. Maybe I need to provide more. Let's ask about the commercials. So what commercials were there? Let's see what type of response it gives. Okay, I guess it does not have a response for that, but I guess it did get the celebrities, which was good, and we did not get that out of the long context length from Gemini. And we're using Gemini as well right here. Just the way that we're doing it is either putting it directly into the prompt or using RAG. So there's kind of two ways to do it. I think someone else at SingleStore did a presentation on is RAG dead, or it might be in the future. I think it might be in the past. So it might be an on-demand webinar that you can watch. Kind of really, comparing the differences between this 2 million context length that you get from, some of these large language models versus this technique that we've been using for a long time, last year or so, called retrieval augmented generation. And yeah, we can go straight into questions now.
That
Yeah,
was really fun, Ayush. Thank you so much. Such a nice demo.
Thank you.
Akmal, do you see any questions that you want to bring up?
there's a couple that are outstanding there, as you can see, 4 open questions at the moment. If I pick on the first one that I can see from Craig, it says, what is the source of these benchmarks? I think you referred to some benchmarks in your presentation slides, Ayusha. Where are they from, basically?
Yeah, so I don't remember the exact website. Basically, if you search like LLM benchmarks, you'll probably find it as a
Yeah.
first result. I can actually link it directly in the GitHub, so that you guys can access it
Yeah,
later.
that'd be great.
Yeah.
Okay, brilliant. Thank you. Thanks for that.
For all of you guys, the Q&A button is at the bottom of your console. You guys can ask us any questions that you might be facing right now. We do have some open questions right now, but please feel free to put them in the chat and we'll take it up. We have one question from Manoj. He says that, is it okay to use OpenAI embeddings on Gemini?
Yeah, so that's a great question. And yeah, it's totally fine to use based on what you're doing, right? So in this example, actually, I use OpenAI embeddings. And if you're doing retrieval augmented generation, where you're just using the embeddings to do a vector similarity search into a vector database, then it doesn't really matter like which one you use. It's kind of like up to a preference. Do you like Google better? Do you like OpenAI? So yeah, for RAG, it doesn't really matter. If you're doing something more specific that with the Google API, there might be some use cases where you need to use the same one. But specifically for RAG, it doesn't matter which one you use.
Okay, sounds good. We have one question from Chehan. They say that, do you know any benchmark about latency among these big LLMs?
Um, I don't know on the top of my head, but there definitely is. There definitely are some benchmarks on that. If you just do a quick Google search, you'll probably find some because that's a really important thing when you're building out these applications. Latency. You want your application to be quick, so your customers are not waiting too long. So that's definitely something that should be available online. I don't know one on the top of my head, but definitely should look into it.
Awesome. Okay, we have one more question from Chetra. She says that these tools are great, but what about the ethical considerations of these tools? This is a very good question in my opinion.
Yeah, definitely great question. So in terms of like this specific demo, there's kind of, two ethical things I kind of see that might need some consideration here. First is retrieval augmented generation, right? So if you're doing something with RAG when you're trying to make a chatbot that's based on user data, right? So essentially your RAG model would basically do really customized responses to customers based on their data. So it goes through their data, their personal data. That can see something where you need to have some ethical considerations. So like, how do you make sure their privacy is safe while using these models? Are these models secure? And like a lot of times it's really important. That's why these open source models are really, really important to have, for developers, for companies, because You don't want to be sending these requests with these sensitive user data back to like OpenAI or Google or these other companies when they're going to use that data to train their own models. That can be something that's very bad. And so you want to have something more secure where, and especially when you're doing RAG on customer data, where especially you could be using your own local model or something where you're using an enterprise model where they don't actually train on the user data. That's super important. And another thing to consider is for multimodality. It's really important to, if you're doing image generation, video with their Sora model from OpenAI, there's a lot of ethical considerations there to consider. How can you prevent misinformation and like bad usage of these types of models? Great question, and I think it's an ongoing question in the community, but I think it's something to definitely consider.
Sounds good. We have one more question from Chehan. They say, how do you limit the response to a specific word count? Are there parameters that in some of the presented LLMs? I think I'll just rephrase that. Are there parameters for that in some of the presented LLMs?
Yeah, so there's not specific parameters for word length in the models, but there's something called I think context length. They're not I believe it's input tokens. There's a parameter for OpenAI and Google where it's basically you can specify how, or sorry, not input tokens, output tokens. So you can specify how many tokens the model will output. Now this doesn't completely translate to words, and sometimes what happens is the model cuts off based on they cut their sentence in half to meet that requirement. So as of right now, there's not really a word limit, and I agree. Like there's not really a good way of doing with prompting right now. GPT it doesn't know it doesn't really have a good sense of number of words as of right now. But yeah, that's like one parameter that you could use.
Sounds good. Thank you guys for your kind words. It really means a lot to us that you guys like the presentation. We'll take one more question before announcing the raffle winner. Akmal, will you like to pick a question?
Oh, I was just answering the question. Kyriakos answering, you compared the most famous LLMs about their performance in Python coding. How about Java coding? Good question. I was just going to say that I've used Java unofficial support for OpenAI. So OpenAI actually has a page where they list these kind of community efforts for other languages beyond Python and sort of JavaScript, for example. And I suspect that this is probably going to be the case with the other LLM vendors as well. You'll just have to dig around and find something. But once you have that, I mean, it works really well. And I've done the same thing recently for R as well. I found something that's community supported, although it's unofficially supported by the the company itself. So it's unfortunate, but there we are. I mean, I know Java is still important. It's an enterprise language, still widely used within corporates, but Python seems to be the most popular at the moment, probably because in terms of data science and machine learning and the packages it supports. But
yeah, thank you, Akmal. We are actually a little, almost at the end of the webinar. So, Ayush, if it's fine, should I go forward and announce the raffle winner?
Yeah, sure.
Absolutely. Guys, we'll follow up with each and every one of you after this webinar, and we'll try to answer all of your questions. Anyway, if you guys want to reach out to our team, you can, go to the chat, and I've put our email address. That's hello@singlestore.com, and you can reach out to our team with any questions that you guys might have. So thank you, Ayush. It was such an amazing session. I kind of I'm remembering my own coursework. It was so academically inclined, really, really cool. So guys, quick notes before we announce today's raffle winner. We have several amazing sessions coming up. On May 20th, we have how to build local LLM apps with Llama and SIngleStore for max security. We'll have Akmal as our expert for that webinar. So please make sure to join this webinar. He's a great speaker. On May 17th, we have a very in-demand webinar that's GPT-4o for developers. Hands-on with OpenAI Spring Release API. Make sure to tune in or just register, and we'll send you guys the recording after the webinar ends. And tomorrow we have Beginner's Guide to RAG with Professor Tom. Amazing session. I really want you guys to RSVP right now if these topics are interesting to you. And All right, moving forward to the announcement everyone's been waiting for, the raffle winner. So we have a very special winner today. Today's raffle winner goes to Bill Peebles, who is a research scientist at OpenAI. Thank you so much for joining, and we really appreciate you guys. And guys, if this is not you, please do not give up. We are also going to announce one more AirPods winner by the end of the day who has tried out today's demo by signing up at the raffle link that I had put in the beginning of the chat, and anyone will be eligible to and be entered to win. Thank you so much, Ayush, for today's presentation and demo. We really value your time and energy, and such an amazing demo that was there. It was so cool to see. And thank you everyone for joining, and have a great rest of the day. Take care, everyone. Bye-bye.